All right, so let's start. There's quite a few slides to cover today, so let's go through it. Just before we start, just to remind you what we've done on Tuesday. We read through the course outline and we talked about the various stuff. I hope everyone's got the lab manuals by now. If not, please go to the bookshop today. Don't let them run out of copies because you won't be allowed in the lab if you don't have a lab manual with you. Also, another thing with the lab, there's a strict rule coming into the lab. You must have closed-toe shoes. So no thongs, sandals, or any open-toe shoes when you come in. If you do come with them, you will be asked to leave, and there's absolutely nothing we can do about it. We are instructed by the school to not let students in with open-toe shoes. Please keep that in mind. If you want to wear open-toe shoes before and after your lab, that's your thing, no problem. But have closed-toe shoes with you when you come to the lab. Unfortunately, the demonstrator will be very strict about it, so please just come with closed shoes. Okay, other stuff that we've talked about, I mentioned there are going to be quizzes starting from next week. I will tell you a whole lot more about it on Tuesday. When we have the Tuesday lecture, and then clarify any less things if you want. Other than that, I think everything should be all right. Any other questions before I continue about the course outline, anything we've done Tuesday? Yeah. Okay, so in the Tuesday lecture, we sort of introduced digital systems. We roughly said why we're here. I gave you some example of digital systems that may or may not have been clear. And then we had a little discussion about positional number systems, why we're using base 10 or 10 digits. Please shut up. Please shut up. And today we're going to talk a whole lot more about number systems. We'll concentrate on binary number system because this is what we'll be dealing with mostly in this course and later digital courses if you do them. And talk about some other binary representations, not necessarily for binary numbers, but what we call binary codes, grade codes, BCDs, but we'll get there. Okay, so back to our example, we said we count in base 10 using 10 digits. And if you want to start formalizing what does it mean to count in base 10 and do mathematics in base 10, take the number 724.5. And then we can actually say that this number is really a combination of 7 times 10 to the power of 2 plus 2 times 10 to the power of 1 plus 4 times 10 to the power of 0, and then continuing this logic, 5 times 10 to the power of minus 1. Now this is fairly simple arithmetic. It'll just be 700 plus 20 plus 4 plus 0.5. How much is 10 to the minus 1? 10 to the minus 1? 1/10? Yeah? 5 times 1/10 is 5/10, which is a half, 0.5. We add them all together, we end up with our 724.5. Now, when I wrote this number there, you see this little 10 here? That represents base 10, and this is the convention that we'll use. If you see a little subscript of a number, that means what base this number is represented in. So nothing special so far, but let's go and talk about other bases. Let's take a number in base 5, the number 312.4, and then a subscript of 5. Now, when I talk about base 5, the first thing you have to think about is we only have 5 digits. So we can really only count 0, 1, 2, 3, and 0, 1, 2, 3, and 4. 5 digits, yeah? It works out. So this number cannot actually have like 372 because there's no such thing as a 7 in base 5. But if I want to know what number is this in base 5 equal in base 10 in the sort of world that we know, We can do the break just like we've done up there, but now those powers will be powers of 5. So it will be 3 times 5 to the power of 2 plus 1 times 5 to the power of 1 plus 2 times 5 to the power of 0 plus 4 times 5 to the power of minus 1. 5 to the power of 2 is 25 times 3 is 75 plus 1 times 5 is 5 plus 5 to the power of 0 is 1 times 2, so it's 2 plus what's 5 to the power of minus 1? So 4 5s, which is 4 fifths, yeah, 0.8. We add them together and we get 82.8, which hopefully is the right answer. Now, this 82.8 is in base 10. Now, if you're really picky, you'll realize that all the arithmetic I've done there is actually base 10 arithmetic. And this is the method we'll work with because we're good at base 10 arithmetic. I don't envy you if you know arithmetics in other bases off the top of your head. By the way, they promised me that air conditioning will work today. Maybe. And this is, in a way, how we convert between values in different bases to the value in base 10. Now, if you want to formalize what I just showed you, then we can talk about position number system with positive radix, which is what we'll deal with, is numbers represented with digits, and we'll call those digits A0, A1, and so on. And we can have fractional parts, so A minus 1, A minus 2. Each one of those digits can only be a digit between 0 and the base that we're talking about. So if we said the base was 5, we only have the digits between 0 and 4. The point is the radix point. In decimal, it will be the decimal point, but it could be in any other base. And then we get the fractional part. And then you can sort of formalize it in this formula, which looks messy, but it really is not, where you express the integer part and the fractional part. So this is just a formalized definition. I think it should be clear sort of what's going on here. Now, as I said, in this course, in digital, in general, we'll deal mostly with binary numbers. Binary numbers are base 2, meaning we only have 2 digits, 0 and 1. Those digits, we call them bits. You probably heard this term before. Bits, if you didn't know, stand for binary digits. That's actually where it came from. Now, when we talk about binary numbers, it's very convenient to define 2 terms, the least significant bit and the most significant bit. So if we have a binary number such as, let's take 101101, whatever favorite binary number you have, then the rightmost bit will be the least significant bit. The leftmost is the most significant bit. And you will come across these terms quite often. They're very simple, just so you know what we're talking about. Any questions so far? Moving on. So we said how we convert from different bases to base 10, and that applies for base 2 as well, or binary. We can take an example of a number and then see how we convert this to base 10. So the highest power that we'll have, if we start counting, that will be power 0, 1, 2, 3, and 4. So what it is really is 1 times 2 to the power of 4 plus 1 times, please turn off your mobile phones, 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. 2 to the power of 4 is 16, 2 to the power of 3 is 8. This will be zeroed out anyway. to the power of 1 is 2, zeroed out. 2 plus 8 is 10 plus 16, 26 in base 10. Everyone agrees? Cool. Now, as you saw, I actually added in those zeros that eventually get zeroed out anyway. In practice, when we actually work with these things, we don't care about the zeros. We really just take all the positions of the ones and add the power of 2's, which makes things a bit easier. Now, the way I like to work with converting binary numbers, because I can't just look at a long binary number and see what it is off the top of my head, then I'd like to write the powers of 2 just above those digits and then add them together. So this will correspond to a 1, a 2, a 4, an 8, 16, and 32. And sort of on the same logic, this will now be a half, this will be a quarter, yeah? To the power of -1, to the power of -2. And then it makes it really easy, because then I can just add 32 plus 16 plus 4 plus 1 plus a half plus a quarter, and hopefully I didn't forget anything. I didn't screw it up? No? Good. Which is 32 plus 16 is 48 plus 4 is 52 plus 1 is 53.75 in base 10. So if you're given a binary number, yeah?
I was saying forget that base 10 subscript. We get marked down.
No. If it's, well, look, usually we write those subscripts if the context is not so clear, right? If I see you do something like this, I'll know you're putting a base 10. You're converting to base 10. I'll know what you're talking about. Clearly, this is not binary, and probably base 10. We will, most time, now I'm sort of emphasizing this just to show you the notation. In reality, if it makes sense, and don't put it there, but if the context is not so clear, if you're working with a few different bases on the same page, then it probably makes sense to put the base here. Yeah? One other thing, by the way, in this course, don't be too concerned about marking and what you're getting assessed on. Well, obviously you should be worried a little bit, but I like to think that we're here to enjoy digital design and all that, not so much be here to get high marks. I mean, obviously you should all get high marks, but don't let this be your biggest worry. If you enjoy this, you'll get high marks. Easy as that. Other questions? And by the way, we are all sensible people in this course. If you do something that's obvious, we'll figure out it's obvious. We're not that crazy. All right, so what I showed you before, that was writing all those powers of 2, is because I work with binary a lot and I know what the powers of 2 off the top of my head. And because you're going to be working with binary a lot as well, you should remember them off the top of your head as well. Now, a lot of these are the first 10 exponents of, 11 exponents actually, of base 2. Most of these numbers should be fairly familiar to you because they come up, all these numbers come up usually in relation to computers and anything that's sort of involved binary. And you must have seen those files before. It's really good idea. In fact, it's probably mandatory to remember at least the first 10 or 11 exponents. And then you can continue from there. I could probably remember off the top of my head up to here. After that, I have to start looking it up. If you can remember more, great. It will make your life a whole lot easier. But that lets you do things like, if you want to do conversions, you just put the numbers at the top. Makes things easy. Now, speaking of computer language, we have this terminology. You must have all seen it before. for special powers of 2. So 2 to the power of 10 is a kilo, as in kilobyte. 2 to the power of 20 is mega. 2 to the power of 30 giga. And 2 to the power of 40 is tera. So, you know, you buy 2 terabytes hard drive, and you have a modem that's 28 kilobits per second because you haven't upgraded yet, and so on. So the thing to realize is that those terminologies, the kilo, mega, and so on, actually kind of clash with old terminology that we had for kilo and mega and all these words, such as if you think about a kilogram or kilovolt, which really means 1,000, not 1,024. And this is a bit of a place for confusion, because when you talk about kilobytes, do you mean 1,000 bytes, or do you mean 1,024 bytes? When you buy an iPod and they tell you it's 16 gigs, is it 16 those gigs, or is it 16, what is a gig? Trillion? Yeah. 16 trillion bytes. Because you know, you naturally think it's 16 gig, you get a whole lot of gigs, and then you plug it to iTunes, and then all of a sudden iTunes tell you, yeah, you've got 14.3 gigs, and then you feel like you've been cheated. And then you look it up and they say, yeah, the operating system takes a little bit of space, but you know, that's probably 200 megs, still not add up to 16 gigs. And then you look it up and then you see the fine print that says on the iPod that 16 gigs mean 16 trillion bytes, not 16 times this. And then you're really angry, but then you get over it. Now, just to distinguish between those two sort of terminologies, there's a committee called the IEC, the International Electrotechnical Commission, that back in 1999 came up with new terminologies for powers of 2. So they said, we'll reserve these for powers of 10s. For power of 2, we'll call it, instead of kilo, we'll call it kibi. And on the same logic, mebi. Sorry, that's actually mebi. Gibi and tebi. So you start having things like kibibyte, mebibyte, gibibyte, and so on, which should mean powers of 2. Anybody heard these before? Yeah, of course not. Nobody uses it. But it's there. If you do run into those terminologies, know that they're what they're there for. Again, not really widely used, but what they really mean is powers of 2. Okay, so we learned how to convert from a binary number into a decimal number. So if you're given a binary number, we know how to, we know its value in decimal. How do we go the other way around? So suppose I give you a number in decimal and ask you what's its binary value. And you know, if it's a small number, you'll know it off the top of your head. If it's a large number, you're going to have to convert it probably manually. So how do we do it? We take our number, and let's take an example of 41. And we keep dividing it by 2. Then we split into the quotient and the remainder. So 41 divided by 2 is really 20 with remainder 1. And then we keep iterating and keep dividing the integer parts, the quotient. So we'll keep going. 20 divided by 2 is 10, remainder 0. 10 divided by 2 is 5, remainder 0. 5 divided by 2 is 2, remainder 1. Yeah, everyone's with me? 2 divided by 2 is 1, remainder 0. And one last step, 1 divided by 2 is 0, quotient, remainder 1. Once we hit 0 here, we don't go any further. And then we look at this column of remainders, and we're going to read it from the bottom up. And this is going to be our binary representation for the number. So this will be our most significant bit. This will be our least significant bit. And then we can say that 41 base 10 is 101001 in base 2. Now this is true for any base, by the way. In this case, we kept dividing it by 2 because it was binary. We keep dividing it by the base. But if I gave you a number, say, in base 7, such as, or I ask you to convert a number to base 7, sorry, we'll do the very same thing, but keep dividing it by 7. So let's take another number, 388, divided by 7, and this is where I'm going to need your help. Five remainder.
No, 55.
55, and then remainder. Remainder 3?
Yeah, 3.
3? 3? Yep. Okay. And then, luckily I can continue from here. 55 divided by 7 is 7, and then remainder 6. And then 7 divided by 7 is 1, remainder 0. And then 1 divided by 7 is 0, remainder 1. Remember, we keep going until we hit the 0 here. Yeah? Not a 1, but the 0. Same idea, we read it from the bottom up. Now it's going to be, oops, where are we? The most significant digit rather than a bit, because it's a digit, this significant digit. And then I can say that 388 in base 10 is the same as 1063 in base 7. And by the way, if you think about it a little bit, the digits that you will get in a new base will never actually be more than the base itself. So here we're talking about base 7. You will never get a remainder that is actually larger than 6. So this process will sort of restrict us from actually staying in the base. I mean, as you would expect, I would be very worried if we get like 1093, because then it means someone screwed up the mathematics. Probably me. So this is how we'll convert numbers from decimal to any other bases. We will mostly use it for binary conversions in this course. So remember the process. You keep dividing by 2, take the quotient, the remainder, and then you just read the remainders from the bottom up. Now this thing that I showed you only works for integer numbers, so no fractional parts. What if we want to convert fractions from decimal into binary? In this case, we'll do a similar process, only this time around we'll keep multiplying the fractions by 2. And then we'll separate it into an integer part and the fractional part. I'll show you in a second. We'll keep multiplying the fractions and keep writing out the integer parts. Let's see how it works. As an example, let's take 0.6875. We'll multiply by 2. Help. 375. So we will write out the integer part is a 1. So I'm looking at this integer part. And then in the next step, I will keep multiplying just a fractional part. So we'll take now 0.375 and multiply by 2, which will be 0.75. The integer part is a 0, so I will write the 0. And I'll keep going. This will be 1.5. So the integer is a 1. I keep multiplying the fraction, and I get a 1.0. So the integer is a 1. But once I get to this 0 here, so 0 fraction, there's no point keep multiplying zeros, because we will just end up at 0 all the time. And this is when we stop, when the fractional part is a 0. In this case, instead of reading it from the bottom up, we'll read it top down. So we read this from here, so most significant bit, least significant bit. And now I can say that 0.6875 in base 10 will be 0.1011 in base 2. Make sense? Questions? Now, I said I stop when the fractional part is 0. Sometimes you won't be so lucky to get to 0 after 4 steps. You want to actually keep multiplying those fractions again and again, and this string here will keep going for a very long time. Sometimes it will keep going forever. This will happen when you start having repeating patterns. I'll give you an example. If you look at, it's a lot of text, but this is what I pretty much said. If you look at trying to convert 0.65 into binary, you will start getting into a pattern where your multiplication will be the same. After 4 steps, the same numbers will come up. This will generate an infinite number of binary digits after the binary point. And then we have to figure out what do we do then. I mean, you can keep going and do the multiplications. Hopefully you will identify that you keep repeating yourself, and then you can stop there and you can say, all right, this is the repeating pattern. But how do we actually represent the number? So there's a few things. First of all, if you see a repeating pattern after a while, then great. You take the repeating pattern, and just like in decimal notation, you can put a bar above the repeating pattern, or dots, depending how you learned it in high school, above the digits that will symbolize that this is a repeating pattern. Otherwise, and it's not, to tell the truth, it's not something we usually do. Otherwise, we say, okay, we want this number to be accurate up to, say, 10 binary digits after the point, and then we'll either truncate or round this number there. Truncate means just cut it where it is. Round is just like decimal rounding, saying if the next bit would be a 0, then keep it a 0. If the next bit is a 1, round it up to a 1. Either way, either truncate or round, depending on the application, really, by the way. How do we choose which one? Well, depending on what you want to do. Okay. Is this point clear, by the way, that we will get into repeating patterns sometimes? Yeah? Good. Now, what I showed you so far was how we convert from binary to decimal. I showed you how to convert from decimal to binary. I actually said this applies to all bases. So instead of multiplying and dividing by 2, you just use the base. So you either divide by the base. Same for fractional parts. The reason why I'm not showing too many examples is because we won't use it, but you should understand the idea. Now, what if I told you to convert a number from base 5 to base 7? If you think about it, we didn't actually talk about how to convert between two things that are not decimal.
Get it to 10. You first convert it to 10, and then you go to the next base.
Yeah, that's right. So if we have two bases that are not, one of them is not 10, we will go through base 10 with a few exceptions that I'll show you in a second. So if I wanted to go from base 5 to base 7, I will convert base 5 to base 10, and then base 10 to base 7, which is some stuff we know how to do. Naturally, we'll have to do the integer part separately to the fractional part, so in the methods we just learned, and then we just join them with a point in the middle. Now, if you want to be very pedantic about it, the only reason why we go through base 10 is because we're really good at base 10 arithmetics. If you knew how to work in base 7 arithmetic off the top of your head, or base 5 arithmetic, you're more than welcome to do the conversion directly. Trust me, it'll take you a whole lot more time and probably make a whole lot more mistakes to just go through base 10. And that's the easiest. Now, we said that any base will have as many digits as the base, so base 7 will have 7 digits, 0 to 6. What happens when we have bases larger than base 10? What if I talk about base 12? So obviously 12 digits, 0 to 12. What's the 12 digit? In this case, if we need more than 10 digits, we'll start using the English alphabet or the Latin alphabet. So A will represent the digit 10, B will represent 11, C 12, and so on. And this will actually take us to a bit of a discussion about hexadecimal. Now, again, in digital, in this course, we will really only concentrate on those 4 special bases. Binary, base 2, octal, base 8, decimal, base 10, and hexadecimal, base 16. More than that, we probably won't touch octal too much. So this leaves us with binary, decimal, and hexadecimal, which is great because it's not that many to remember. And they're all related to each other. So what I just said, in hexadecimal, we have 6 additional digits that we need. And we will use A, B, C, D, E, and F for them. A being 10, B 11, F being 15. Now, as a convention, when we write a hexadecimal number, we will use the prefix 0x to represent it's a hexadecimal number. And then in this case, you don't have to put the base 16 at the end of the number. This shows us it's a hexadecimal. As an example, 0xA5 will be the number A5 in hexadecimal. And you can quite happily convert it to decimal, by the way. A, we said, represented 10 times 16 to the power 1 plus 5 times 16 to the power 0, which is 165, hopefully. Huh?
165.
Yeah, I got it right. So I didn't do anything special here. I just realized that A is the 10 because we said these will be in decimal arithmetic. This position here in base 16 will be the power of 1. This position in base 16 will be the power of 0. Nothing special. Everything we've done so far. Now, as I said, these are the 4 bases we'll use the most in this course. And it's really important that you actually remember the first 16 values. Because, well, first of all, I mean, it's a good idea if you don't remember it already to sit at home, stare at it for a while, and then try to see if you remember it. Even if you don't, trust me that by the end of this course, you will know it off the top of your head, like it or not. Specifically, I want you to know any binary representation, how it converts to decimal, instead of doing the conversion on paper manually all the time. And the other way around, so if I give you a decimal number, what's its binary representation? Don't worry too much about octal. Be very careful to say it, because I'm not supposed to tell you that you shouldn't be worried about things. Don't worry about octal. See my punishment? Hexadecimal, important. So the conversion between hexadecimal, binary, and decimal, please remember. Why is it so important? Because it's really easy to convert between binary and hexadecimal and octal as well. Those 3 bases are very much related to each other. Now, if we want to convert between binary and, say, hexadecimal, or the other way around, we don't actually have to go through base 10. We can do a direct conversion, and the way we do it, and I'll show you an example, is that if we want to go from, say, hexadecimal to binary, we will state each hexadecimal digit as its equivalent 4 binary bits. So every 1 hexadecimal digit into the 4 binary bits. And then to convert back, if we have something in binary, we will group groups of 4 bits, and we'll be able to get and have a direct conversion between each group to hexadecimal. And this is true for octal as well, only in octal we use 3 bits per digit. And let me show you an example because it will make life a lot easier. So we have a really long number that I really don't want to convert through base 10. And I'm being asked, first of all, I'm being told this is a base 8 number, an octal number. And they want me to convert it to hexadecimal through binary. So I will have to convert this to binary and therefore to hexadecimal. It's actually really easy. I'm always starting from the middle, from the binary point, and I'm moving both ways. So I will start here, and I'll start with the integer part. So I'll take, again, these are octal numbers. Each octal number is represented by 3 binary bits. The number 3 in binary will be 0, 1, 1. Number 5, and I just keep writing them next to each other. 5 is 1, 0, 1. 1 is 0, 0, 1. Remember, I'm always using 3 bits, always, for this conversion. 6, 1, 1, 0. And 2 is 0, 1, 0. You will remember it off the top of your head in no time as well. Going the other way, we'll put the point and then go 7 is 1, 1, 1. 4, 1, 0, 0. 0 is naturally 3 zeros. And 6 is a 1, 1, 0. So this is this number in base 2. See, I didn't even have to go through base 10, no multiplications, no divisions, straightforward conversion. As I said, you will remember the mapping between binary and octal and hexadecimal in no time, and you'll be able to do it easily. Now that I've got my binary number, I want to go back to hexadecimal. So I said hexadecimal digit correspond to 4 binary bits. I will start grouping them in groups of 4. So I'll take my binary number, and I'm starting from the middle, from the binary point. Not necessarily the middle, but rather from the point. And I'll make as many groups of 4 as I need. In this group here, I've only got 3 bits. There's no problem padding it with another 0. If you add a 0 in front of a number, you're not actually changing its value. No problem there. And also the other way around. And now I will take each one of those 4 bits and convert them to hexadecimal directly. 1, 0, 1, 1 is a B. 0, 1, 1, 0, 6. 1, 1, 0, 0, C. 0, 0, 1, 0, 2. Point. Correct me if I'm wrong, by the way, because I don't always get it right. 1, 1, 1, 1. F, 0, and 6. And then I'm just putting it all back together. So this number here will be the hexadecimal 2C6B point F06. Yeah? Any questions so far? Yeah?
So can you add zeros at the end of the decimal?
Yeah. Same as you would in binary, in decimal. Adding more zeros at the end doesn't change the number. By the way, one thing I forgot to point out, in every section there's a reference to the book. So if you read something in the lecture notes, you're not quite sure what's going on, you can go to chapter 1.4 in the book and find the relevant information. So just so you know what those boxes up there mean. Now, back to the statement that in digital we're concentrating mostly with binary numbers. We will work a lot with binary, but not necessarily always with numbers. What if we want to design a system, a digital system, that would deal with something else, not necessarily numbers? I don't know, let's say flavors of soft drinks. I don't know, just a random example. That I want to represent every different flavor in my digital system. In this case, I will have to give a code to each flavor. So Coke will be 001, Sprite will be 010, and I can keep coding them as I want. So this is the difference between representing numeric types and non-numeric types. When we talk about numeric representations, we usually want to represent them in binary in as close of a mapping to the actual numeric value as we can. So if we're talking about decimal numbers, we usually will map every decimal number into its binary equivalent. This will let us do arithmetic operations on the numbers, and it will make the mapping very easy, very straightforward, easy to work with. When we have non-numerical types, such as, I don't know, flavors of soda, we can start mapping it any way we want, because there's no restriction that Coke must be a 001 and Sprite must be 010. It depends on the application, depends what we want to do. So it gives us a little bit more flexibility, but depends what we want to do with this. And as an example, I will represent, how many colors do we have? 7 colors in the rainbow using 3 bits. So in this case, n, the number of bits, will form our code words. And I will map every code word to a distinct color of the rainbow. Now with 3 bits, how many different combinations can you have? 8, yeah? Anybody knows how they brought this huge crane into the main walkway? No? Anybody seen the huge crane in the walkway? How can you miss it? It's massive. So with 3 bits, I can represent 8 different codes. I've got 7 colors. I will map a distinct code to every color, and I've got one spare one that is not being used. Why did I choose the spare one as this one? Because no good reason. Maybe there is a good reason, but we will talk about it when we start actually implementing circuits. How do we choose which codes to map to what word? Now there comes a question of how many bits do we need to represent any set of items. In this case we had 7 colors. We could have used 3 bits, because with 3 bits we can represent up to 8. We couldn't use 2 bits, because 2 bits will only give us 4 different combinations, and then we won't be able to represent all of them. So if you want to formalize it, the number of bits you will need to represent a set of m elements will be the ceiling function of log 2 of m. Eek. It's not that complex. See, if we had 50 items, what's log 2 of 50? Quick. Huh? Roughly? 6 point something? No, 5 point something. So log 2 of 50 is 5 point something. The ceiling function will push us to 6. So we'll need 6 different bits to represent 50 different items. We will have some leftovers. 6 bits, by the way, will let us represent 64 different items. We can use 50 of them to represent 50 items. If we use 5 bits, we can only represent 32 items, not enough. So we'll always have to go equivalent or over what we need. Question, how many bits do we need to represent the 10 decimal digits? 4. Yeah. Log 2 of 10 is 3 point something. Ceiling of 3 point something is 4. In fact, with 4 bits, we can represent 16 different items. We only need 10, so that works. We couldn't go down to 3, because with 3 bits, we can only represent 8 things. You can actually generalize it, not necessarily to binary. This is the formal so definition. If you're working with base R, you can and you have n digits, you can represent up to r to the power of n different items. Again, we will usually work in binary in this course. With base binary and 2 digits, we can have 4 different combinations. So we 0, 0, 0, 1, 1, 0, 1, 1. If we had 4 digits, we can represent up to 16 different items. But we really only want to represent 4. Let's say we'll give a mapping of 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. So 4 out of the 16 different options, I will map those 4 into my elements. What's special about this coding? You can see that the 1 keeps jumping places. This kind of coding is called one hot. It does come in useful. This is why I want to share this example. So sometimes we want to introduce redundancy in the number of bits that we have in order to simplify other parts of the circuit. Now, it will come very handy to code the decimal digits. So obviously we can have binary conversion between decimal between decimal and binary, but sometimes it is easier or makes more sense to actually code those decimal numbers. What does that mean? It means that we will take every digit in a decimal number and give it its own code, rather than take the whole number and convert it. Now, there's 2 methods I'll show you in a second. BCD, binary coded decimal, and the other one is gray code. Let's talk about BCD. In BCD, we take the binary value of every digit from 0 to 9, and we have a direct conversion for every digit. So if I wanted to represent 185 in base 10 as a BCD coding, I will take each digit. I'm not doing conversion. I'll take each digit and write its coding using 4 binary bits. So 1 will be 0, 0, 0, 1. 8 will be, it will be 1, 0, 0, 0. 5 is 0, 1, 0, 1. And this is going to be our BCD code for 185. It's not the same as the conversion we've done before. If we want to convert it, and this is something I prepared earlier, we will end up with this number. Okay? You know these stuff, but you want to see?
Is this?
No, 2141. It's done it last year. Okay. So again, not the same thing. This is conversion. This is coding. Let's talk about gray code. In gray code, and this is not necessarily just true for coding decimal digits, gray code in general, whenever you hear the term, it means that the difference between any 2 successive elements in your set will differ only in 1 bit. So if we go back to our example in the table of how I want to represent the decimal digits, and you look at this column here, you'll see that between any two successive elements, there's only one bit change out of the 4. So in the first one, only this bit changes, and then between this one and this one, only this bit changes, and then this bit, and so on and so on. And it actually wraps around as well. So from 9 back to 0, again, there's only one bit change. So this is sort of from the example I showed before. So 3 in gray code will be this. 4 in gray code will be this, and there's only one bit change between them. If you took the regular binary codes, between 3 and 4, you actually get 3 different bit changes. Yeah?
Is there a trick to creating gray code so they wrap that around?
Yeah. Two things about gray codes. One, there's not one distinct way of representing a set with gray code. You can come up with more than one series that will have these properties that only one bit changes. You can, in order to come up with coding for any given set, you can always start naively to start with something and then change one bit at a time. Then you get usually to about the 9th one, and then you realize that you're stuck because you already used all the represents with one binary change. And then you panic, and then you go online, and then you find the algorithm that actually does it for you. So there is an algorithm to do it. I didn't write it here. It's not that important for our purposes. But if you do want to come up with a gray code encoding, there is an algorithm. You can just put in how many elements you have, and it will spit out. And when I say algorithm, it's not like a computer program. It's actually a description of how you go about coming up with those representations. Again, there's more than one distinct way to do it. Why is gray code good for? Let me just give you an example. Imagine this thing that's called an optical shaft encoder, which is a round disk that spins. Now you're going to have to use your imagination a little bit here. Imagine there's an axis just through the center, and this thing spins. Now I want to give it a spin, and then when it stops, I want to know what angle from 0 is this disk standing on. The way I'm going to go about doing this, I'm going to put clear parts on my disk and some mask parts. And I'm going to have a light source on one side of the disk and then light detectors on the other side. Any place on the disk which is transparent, which is clear, the light will go through. Any part of the disk that is masked, the light will be blocked. Now, if I define the 3 regions on the disks to be bit 0, bit 1, and bit 2, and then I can say anywhere that the light goes through, it's going to be a 1. Anywhere that it's masked, it's going to be a 0. And then I give it a spin, and then I measure the 3. I check the sensors to see what reading they've got, and then I can say, within some error, which part of the disk I'm standing in. Is this principle clear? What I'm trying to do here? And then, because I know what part of the disk, I can calculate the angle of the disk. Problems start where if I give it a spin and it stops where the light sources are right in the middle between 2 different parts. And this is a very realistic problem. It's not theoretical. You can say it can be either that or that one. If we sort of stop in this area here, then the light in this region may or may not be detected by the other side. There might be slight light coming through, maybe not enough to be detected, maybe yes enough. And in this particular area here, all these 3 regions may or may not be detected. Now, if any of those 3 regions may end up as a 0 or a 1, but I don't know which one's which, if you think about it, I can end up with all 8 different combinations. So if I end up in this specific region here, I have no idea where I am really in the disk, because I can come with any one of those codes. I can fix this by using gray code encodings for any nearby places. So any two areas will only change one with one bit or one mask or clear. And then if I land in some area, say here, then this will obviously go through, always. This will always be blocked. This may or may not go through, which gives me only two possible states, either this one or this one. Now, because I'm in the middle, it probably makes sense to have one or the other. It doesn't really matter. But I won't end up with any of the other sort of directions. So I'm pretty safe on that front. Now, this is just an example of why gray code is useful. You don't have to really memorize it. If you understand it, great. And that's all for me for today. We will see you on Tuesday.